So, in the first part of this lesson, I'm just going to demonstrate why the following is true. This is something that you pretty well much know, but I want to make sure you understand why it's true. So we're going to have a look at this following simple idea, that if I'm looking at the probability of two events occurring, A and B, so probability of A intersect B, it is the same as multiplying the probability of A by the probability of B. Okay, so I'm going to prove that that is the case. So I'm going to do so as quickly as I can, knowing that if you've covered this sort of material before, it's almost revision for you, but it often goes without reflection that the probability of A intersect B is the probability of A multiply the probability of B. So really quickly, I'm going to just set up a simple experiment. And the experiment is just going to be rolling two dice. Okay, so and the first thing I wanted to say is that when you roll two dice, it's effectively a two-stage experiment in that you roll one die. Sorry, I'll put it a different way. That if you have two dice in your hands and roll them, that's the same as rolling one and then rolling the same die again. It'll give you the same list of outcomes, wouldn't it? Yeah? Yeah, there's no trick there. I'm just hoping that makes sense to you, that rolling two dice is the same as rolling a die and then picking it up and rolling it again. Okay, you get the same sample space there. So let's do that sample space. So it's effectively a two-stage. So if I quickly draw up that sample space, I'm just doing it really quickly. I'd have, this is sort of like stage, oops. This is sort of like stage one, and this is sort of like stage two. So when I talk about a multi-stage event or multi-stage experiment, it simply means that more than one thing's happening at the same time, okay? Or one after another, in this case, doesn't really matter. So stage one is going to be a 1 is rolled, a 2 is rolled, a 3 is rolled, a 4 is rolled, a 5 is rolled, or a 6 is rolled. And stage two is that a 1 is rolled, a 2 is rolled, a 3 is rolled, a 4 is rolled, a 5 is rolled, a 6 is rolled. So really quickly, I've got 1, 1, 2, 1, 3, 1, 4, 1. Just putting stage one first, that's all. 5, 1, 6, 1, and so on. I'll just quickly fill out the rest. Tell me if I make a mistake, will you? Leo, tell me if I make a mistake. What? What have I written? Ah, thanks. Is that it so far? Cool, just the one mistake so far. I should go home now. Okay, just purely for my own entertainment, the rest of it. I'm going to zoom out and keep it zoomed out now so we can see stuff. Okay, so good so far? Sample space. Okay, let's now talk about two events. So let's have, I don't know. Let A be the event. And even number is rolled on the first die. Let B be the event. A number less than 3 is rolled on the second die. So I don't know if you've noticed what I've done there, but effectively what I've done is I've deliberately and explicitly made A all about the first stage and B all about the second stage. That's on purpose. Okay, so that's a really important sort of crux to what we're doing here. So effectively, the actual event is that I rolled an odd number where an odd number on the first die and a number less than 3 on the second die. That's kind of the overall event. But I've broken it into those stages so that A is one stage of the event and B is the second stage. So all that's on purpose. Now, what I want to do is I just want to focus on what the probability of A intersect would be. A intersect B would be. We know that the probability of A intersect B is when both of those things are occurring. So if I sort of circle in green what event A is, it would be an even numbers rolled on the first die. So that would be this one, and this one, and all of these as well. So green equals event A. Good eye? Red equals event B. And that is an odd, sorry, not an odd, less than 2 is rolled on the second die. So less than 2 is rolled on the second die would be these ones. Sorry, less than 3, beg your pardon. So it would be a 1 or a 2. Yeah? Okay, so the Christmas looking ones, the red and green ones, that would be A intersect B. So we would have A intersect B. Good so far? Okay, that's the setup. Now, we know that the probability of A intersect B is all possible outcomes as a denominator and matching outcomes as the numerator. So if we have a look at all possible outcomes, we could just count the number, right? So we know that the probability of A intersect B is equal to the number of matching outcomes for A intersect B over the number of all outcomes, which is that N bracket E thingy. Okay, so if we look at NE to start off with, I'm just going to try and keep it to this one slide. If we look at the number of possible outcomes, we could count them, right? So it's 36. 1, 2, 3, 4, 5, 6, 7, and 36. Is that okay? If you just literally counted them? But this table format makes it easier for me to count, right? Because I just have to count the number of rows and the number of columns. There's 6 rows, 6 columns. So it's just 6 lots of 6. 6 rows times 6 columns. Yeah? Obviously. If it was a different outcome, like if it was rolling a die and flipping a coin, that'd be 6 times 2. 2 rows, 6 columns, or vice versa. Okay, so just multiplying rows and columns is okay. But I just wanted to point out that that is equal to the number of possibilities just by considering, no, I shouldn't say A, beg your pardon, just by considering stage 1 multiplied by the number of things I consider in stage 2. Okay, so the number, total number of outcomes, this number here is effectively the number in stage 1 multiplied by the number in stage 2. By the way, I've split it up. Okay, what about the number in A intersect B? We can count them. It's easy enough count. I shall do this down here. The number in A intersect B is where I've got both colors So I've got 1, 2, 3, 4, 5, 6. So I've got, 6 in total. Is that okay? I've got 6 in total from a count. But I can also split that count up as well, in that the number of matching columns is from stage 1. So I've got 1, 2, 3 matching columns for even. And then the number of rows I've got that match are 1, 2 from stage 2. Okay, so the number of matches is given by the number of matches from A and the number of matches from B. So effectively, I've got that equal to, I'm glad I'm recording this because this is kind of a messy thing to be writing down. So the number of desired outcomes is going to be 6, which is the number of matches in A for stage 1. Okay? For stage 1, A in stage 1 multiplied by the number of matches in B for stage 2. Okay, so when I limit my thinking to stage 1 and how many outcomes are there in A, there's 3 of them. And when I limit my thinking to what's happening in stage 2 and how many matching outcomes are, there's 2 rows of them. So it's 3 times 2. 3 times 2, which gives me my 6. Okay. So let's put all that together. And I'm going to have to go to another. I was hoping to keep it all onto the one page, but I'm going to have to go to the next page. But I'll just verbalize it, then I'll write it maybe while I've got it here. So you can see that this would give me 6 on 36, but that 6 on 36 can be broken down into these numbers here. So it looks a little bit like this. It'll be 6 on 36, which is actually 3 times 2 on 6 times 6. That's that breakdown into the stages, which is equal to 3 and 6 multiplied by 2 on 6, which is equal to the probability of A multiplied by the probability of B. Okay? So that's why we can conclude that the probability of A intersect B is equal to the probability of A times the probability of B. Now, do note that this is what is the probability of getting an even number on the first die, and this is the probability of getting a number less than 3 on the second die. So these are pulling from different sample spaces effectively. This is the big sample space. I know I can simplify fractions, by the way, but that's not my point, which is why I'm not doing it. This is from the big sample space. These are from the smaller stages sample spaces, but they are equivalent as a result. Good, good, good? Okay, so the probability of A intersect B is equal to the probability of A multiplied by the probability of B. Except, let's have a look at this example here. Shall I go for the classic? I'll go for the classic. I'll make it easier. Okay, a bag of balls is made up of 3 red, 2 black, and 1 white ball. A ball is drawn but not replaced. What is the probability of drawing 2 red balls? Easy enough. Now, if we used our logic here, we would say the probability of red and the probability of red again. Okay, so there are 3 red balls in the sack. So we would say that 3 and 6 would be the probability of red. And then we multiply it by 3 and 6, which would give me 9 on 36, which could be simplified. But it's not correct. Okay, so even though I've correctly articulated that there is a 3 and 6 chance of pulling out the red ball, on the second stage, my probability has changed. Okay, because once I've pulled out a red ball, the chance of me pulling out a red ball again from the sack has changed. Okay, probabilities have changed on the second draw, because when I want to pull out a red ball on the second drawer, I've got only 2 red balls from which to choose, and there's only 5 balls left in the sack. Okay, or the bag. If I replace them, I would have 3 red balls left. So it'll be 3/6 on the first pass, and now, whoops, all the way around, 2/5 on the second pass. And that would give me the appropriate result. So there's a 6 in 30 chance of getting a red followed by a red. Okay, as opposed to the 9 in 36 chance. What do you think? Does that make sense so far? Okay, so why does it, and I'll just put here, by the way, which does not equal probability of red times by the probability of red. Okay, so why does it work in the first example but not in the second example? And it all comes down to affect. In the first example, when I was rolling 2 dice, when I rolled, rolling 1 die did not affect what happened with the second die. Okay, so for example, let's just say I had the 2 dice in my hands and I rolled them. Well, I rolled 1 and it's a 5. When I roll my second die, how is the second die affected by knowing that the first die is 5? Not at all. Yeah, exactly, not at all. So hence, those 2 things do not affect each other. We call those kinds of events independent events. Those kinds of events are independent. One event does not affect the other. In the sack of balls thing, though, if I draw a red ball from the sack in the first instance, it affects the second draw. And it in fact affects anything I draw, whether it's red or blue or green or white or black, whatever the colors were. It affects them, because once I've drawn a ball out, then I've changed the number of which I can draw the second pull out. So they are affected by each other. So they are dependent events. One event is affected by the other. And it actually kind of works both ways. So for example, if I told you in secret, I drew out 2 balls from the sack, and I said to you, on the second draw, I pulled out a red ball and I had a 3 and 5, a 3 and 5 chance of getting that red ball, and that tells you something about the first draw. I mustn't have pulled out a red ball because there were only 3 to start with. I've just pulled out I had a 3 and 5 chance then, so therefore I mustn't have pulled out a red ball to start with. So the first event can be influenced by knowing about the second event. And in a linear fashion, I think I've just pointed out that you can see that the first event affects the second event. So they are linked. Those events are linked, and therefore they are dependent events. Okay. So very briefly, so if 2 events are independent, then it is true that the probability of A intersect B is equal to the probability of A multiplied by the probability of B, if they are independent. If they are not independent, then this will not be true. So that bottom line there, which is the product rule for independent events, is also a test for independence. Okay, so if I can show that the probability of A intersect B does not equal probability of A times the probability of B, I can conclude that the events are dependent as well. Now, before I go through a couple of very quick examples, okay, I'm about to test my limits in probability. So let's see if I can get the explanation right to you. Students often confuse mutually exclusive with independence. Mutually exclusive means that 2 events, it is impossible for both events to occur at the same time. Okay. So that's what mutual exclusion means. It means A intersect B is 0. Remember that? There's no overlap. So they're completely separate from each other. Independence says that one event does not affect the other. So what can we say about mutually exclusive events and independence? Here's a multiple choice quiz for you. Are mutually exclusive events independent, dependent, or can't tell? Make your decision. You need to decide one of those 3. We're going to straw poll it. If you get it wrong, you will be marched out. No, you won't really, because if I marched you out, I'd have to follow you. Okay, who thinks that mutually exclusive events are dependent? Zilcho. Who thinks they're independent? Zilcho. Who thinks you can't tell? I'm sorry, was that an emotionally compromising question so it was impossible to actually make a decision over 3 possibilities, just as a gut feeling? Thank you to those who did vote then. For those that didn't. Now, the answer is, assuming that both events are non-zero probabilities, okay, so assuming that mutually exclusive events are dependent. I know, it sort of feels counterintuitive, which is why I said to Joe Boyer this morning, can you explain to me whether they are or not? And then he explained to me, I said, okay, got it. And then I said, wait, can you explain to me again? So he explained to me again and I got it. And it's kind of like this. If you look at the basic premise of mutually, remember how I said I rolled a die, told you that it was a 5, and I said, how does it affect the next roll? And the answer was, it doesn't. So hence they're independent. So let's take a simple mutually exclusive event. I know this is not quite right, but let's just say overcast or sunny. Okay. So if I tell you, so you would say that overcast and sunny are mutually exclusive events, right? But if I told you that today is overcast, what's the probability that it's going to be sunny? 0. It was affected by your knowledge that it was overcast. So therefore, the fact that it was overcast affected the probability that it's sunny. Therefore, they are dependent, not independent. All mutually exclusive events are dependent because knowledge about one precludes the other. Yeah? So therefore, they're dependent. There are exceptions to the rule, and it's when one of the probabilities of one of the events is 0, then you can't make that conclusion. Okay, so that's a really important distinction to get right in your head, and that's how Joe explained to me nice and simply, and finally I understood that mutually exclusive events are in fact dependent, not, as you might presume, independent. Although no one said independent, I was surprised because that's what I presumed. And then I had it explained to me. Okay, so the other thing is, let's have a look at this really pretty result as well. Let's go back to conditional probability, and we know that the conditional probability is the probability of A given B. Now, think back to that dice example now. Remember with the dice, I said, I rolled the first one, told you it was a 5. It didn't affect the outcome. So if A and B are independent, what does the probability of A given B intuitively say to you it would be if they're independent? If A is not affected by B, then the probability of A, given that you know B, is? No one wants to take a crack at it? Just intuitive. I don't care if you get it wrong. What's your intuitive gut feeling there? I'd say if you're not saying anything, it's because you just have not a clue at all. No? Okay, so what's the probability of rolling a 6 on the second die, given that I rolled a 6 on the first die? No change, right? Remember how we've been saying that? There's no change. So is it okay if I say intuitively the probability of A given B would just be the probability of A? This is another test for independence. If you can prove that the probability of A given B is equal to the probability of just A, then they must be independent. There's no trick to that. Does that kind of make sense intuitively now that it's been spelled out? It also supports the product rule. That's intuitively. Algebraically, probability of A given B is equal to the probability of A intersect B over the probability of B. But if they're independent, that means it's probability of A times the probability of B over the probability of B, assuming the probability of B is non-zero. They cancel out just because they do. That's, grade 7 maths. So algebraically, it's supported. Okay, if they're independent, then algebraically A given B must reduce down to probability of A. Okay, so I'll give you a chance to try this one out. Probability of A is equal to 0.3. Probability of B is equal to 0.4. Probability of A intersect B is equal to 0.7. Are they independent? Work it out in your workbook, in your summary. If you're going to be neat, you know the answer. You've got 30 seconds. Tom's gone CBB. Can't be bothered. He's just shaking his head. CBB is the polite abbreviation rather than using another CB something. CBD, slightly less polite. Lucas has nearly finished his breakfast. I thought I'd better give a running commentary for Alice because she'll be listening to this later, so she just needs to know what's going on. Seb's just done a pen drop. Oh, that's a very confident one. Okay, so this is how I would solve it. Probability of A times the probability of B is equal to 0.3 times by 0.4, which is equal to 0.12, which does not equal to 0.7, therefore not independent. There we go, something like that. Yeah, just be careful. I don't like this way of drawing it, of solving it. If independent, probability of A intersect B is equal to the probability of A times the probability of B. That's 0.7, that's 0.3, and that's 0.4, because you're setting up an equality which actually isn't true when you do it that way. So it kind of looks nice in terms of, you know, I'm stating a fact and then I'm substituting in, which sounds very mathsy, but ultimately what you're doing is you're setting up an equation which is false. You know, which is false or something like that, but it just seems a bit untidy. Whereas this version here is just starting off with a bit of a fact and then concluding at the end there. That's just me, I don't know. Okay, so what I might do now, it is now 9:10. I want to introduce trees to you this morning. So I'm going to give you just 20 minutes work on independent events. And then in the last half hour, we're going to have a look at tree diagrams, and I've got some work for you to do around trees. So I appreciate that I haven't given you a whole bunch of examples to draw upon, so you might need to lean upon me for more help. But let's just see how you go. Look, we got exercise 9G on page 354. If you're unsure, start at question 4. If you are okay, start at question 6. And if you're really in the bag with this stuff and it's just effectively you're just revising stuff, start at question 8 and work your way forward. They're fairly decent jump-in points.